picking up with the Z-score example. So the time needed to assemble a particular piece of furniture with experience is normally distributed. So as soon as you hear that, you want to think of that bell-shaped curve with a mean of 43 minutes, that would be mean mu, and a standard deviation equal to 3 minutes, that would be sigma. What is the Z-score for an assembly time of 49 minutes? This 49 would be our x, because x is our variable of interest. This is the data, right? So you want to use that assembly time. That's the variable. The formula for our Z-score is x subtract the mean mu divided by sigma, and just plug in those values. 49 subtract 43 divided by 3 gives us 2. So that tells us that we are 2 standard deviations above the mean. It's a positive number, and so that tells us we're above that. Makes sense. 49 is greater than 43. 43 would be about here, right? 43 and 49 would be way out here, and so we are 2 standard deviations above the mean. So you want to keep in mind when you're talking about the empirical rule only is used for normally distributed data. If the data is not normally distributed, what can we do? So what we do is we use the Chebyshev theorem. So this is when the data are not normally distributed, and this will measure the minimum mass or concentration of data that lie within a specified number of standard deviations around the mean. So it's doing exactly the same thing as the empirical rule, but again, the empirical rule only applies to normally distributed data. Okay, so Chebyshev's theorem says within k standard deviations of the mean, mu plus or minus k sigma lie at least 1 subtract 1 divided by k squared proportion of the values. And so it is not defined for k equals 0 or 1, so it's only good, the support is for k greater than 1. Right, so it is a general theory applying to all distributions, and the calculations are for k equals 2, 3, 4, that's what's given here, and again, k equals 1 is not defined. So k is 2, so the distance from the mean here would be k plus or minus, and then you sub in 2 for k, so k times sigma would be 2 sigma. So mu plus or minus 2 standard deviations will be 0.75 or 75% of the data about the mean, right? It's the central or middle data. Mu plus or minus 3 sigma will represent 89% of the data, the central middle data, right? And mu plus or minus 4 standard deviations is 94% from the mean. So it's the central, and it won't be symmetric necessarily. It could be, but it might not be. It could be symmetric or skewed data, but you want to remember that these values are always plus or minus about the mean. So it will be the central part of the data set. Okay, so moving on to an example. Some data are not normally distributed. If the mean is 38 and the standard deviation is 6, question 1, what proportion of values would fall between 26 and 50? 2, between what two values would 89% of the values fall? So before moving on to the next video segment, try and see if you can answer these 2 questions. We'll pick up.